Today we're going to be discussing capacitance. And I'd hope to be a little bit further ahead in our discussions, but you know how that goes. So in order to fully appreciate capacitance, it's introduced in your textbook much earlier, and I don't like the fact that I bring it up during electric fields because you can't fully appreciate what a capacitor is until you understand that electric potential is a way of measuring energy, and capacitance is all about energy. So we're going to start from the broad theory, and then we're going to go down to how to make one, and then how to calculate. So three things we have to do. And they're not straightforward, but they're not particularly hard. Once we have learned how to make one, and once we can calculate a homemade capacitor, and they're all homemade at some point or another, once we have that, then we can talk about how they are used in a circuit. But before we launch into the entire discussion, broadly, a capacitor is any two pieces of conductor. Any two pieces of conductor will work. And no matter what their shape is, no matter where they are, any two pieces of conductor can be a capacitor. Your job is to take the charges from one of the conductors and move them to another. This means finding a way to pump the electrons away from one conductor and deposit them on the other. This should make one of the conductors electrically positive, while the other conductor electrically negative. Once you've made that happen, once you've displaced the charges, you establish an electric field in a region of space surrounding your conductor. Now, ultimately, there's energy in this electric field due to the separation of charges. And what I mean by that is there's clearly an electron here that, due to the fact that it's in this piece of metal and there's an exposed electric field right next to it, there must be electric potential energy in that charge. We know that because you had to work against a field to get it to this location. If the particle were to be released from the metal, it would convert that electric potential energy into kinetic energy because it will want to move against the field. Now, I'm speaking about electrons here. We know that there's the same discussion could take place for some fictitious positive charge particle. But in circuits, it is the negatives that are moved. So we know that this is actual electrons being moved from one metal to the other. But again, electronics was developed before we knew they were electrons. So the people who were developing these concepts recognized that it didn't really matter whether I talked about negative charges moving to the negative plate or positive charges moving to a positive plate. Once there, the energy was still based on how strong the field was and how much potential energy a particle would have at that plate. This is why it makes sense to talk about the fact that there is likely an electric potential between the two plates, which allows us to calculate how much energy there would be per charge in those plates. Now, the reason why a capacitor has value is, apart from the fact that there's clearly a buildup of charges, all I have to do to utilize those charges is create some kind of conducting path between the two plates. The moment I establish a conducting path between those two plates, there's going to be an equalization of charge. Charge will flow from one plate to the other to equalize the charges that have been separated due to me pumping them away. If I put something in the way of those charges, they will have to do work to pass through whatever it is I put in the way. It could be as simple as a wire getting hot, or as complicated as some kind of circuit that's going to use the flow of those charges to do some other form of work. The basic theory here is that capacitors store energy in a form of a separation of charges that manifests an electric field. Capacitors store energy in the form of a separation of charges that manifests itself as an electric field. So, yesterday, we were talking about how to find the electric potential around a collection of charges. The goal there was to be able to deal with whatever kind of shaped conductor we are given in order to note what the electric potential is due to that collection of charges.
Good morning, please.
So our goal here is to be able to figure out how do we construct a capacitor. I mean, I know that it sounds a little ridiculous since I said any two pieces of metal will do. The truth is, we would like to find a way to emphasize or exaggerate this effect. Meaning, I would like to find a way to store the most amount of energy in the smallest package. That's usually the goal of most electronics. Finding a way to make our electronics as efficient as possible. So, besides the broad definition, we will define capacitance. I want to be very careful about this. This is not the capacitance of an object. This is the definition of capacitance. And I'll explain the difference in a minute. Our any device that we just had here, its ability to store energy is based on what we call its capacitance. Now, the word capacitance shouldn't be lost on you that it's capacity, that we use the same root word here. It is how much charge can be pushed into this capacitor. How much charge can we separate from one side to the other? Sometimes it's easier to do this than others, depending on the shape of the metal and the way it's arranged. We measure that by measuring how much charge is moved per potential difference applied. How much charge is moved per potential difference applied. So an object that is a better capacitor will move more charge with the same potential difference than a worse capacitor. If I have a AA battery, which is 1.5 volts, whatever chunk of metals will move the most charges with my 1.5 volts has the highest capacitance. That's what I mean when I say this is how we define the capacitance. It does not tell me how this particular group of metals will actually behave. The only way I could figure out the capacitance using this formula would be to actually connect the potential difference there and try and measure the flow of charges. That's not how we do it. We'll use this definition, sure, but we spent the last 2 months figuring out the size of electric fields from different types of shaped objects for the express purpose of being able to apply it to this kind of device. That's how we're going to figure it out. We're going to take a look at how the shape of the metal creates an electric field and how much work is done in moving charges against that electric field. That's how we'll figure out capacitance. So we're going to use this formula, but not in the way you probably would imagine. We're not going to actually just grab 2 hunks of metal and see how much charge we can push around. Now, a little bit of station keeping here so that we have some full disclosure. Capacitance is measured in coulombs per volt. It's kind of an odd unit. Coulombs per volt. This has been defined as the farad. The farad is the unit of capacitance. And I know nothing about Mr. Farad. I have no idea what he did, what he worked on. I assume he worked on capacitors. Not read any of the works about Farad, nothing. So Faraday, know a lot about him, but maybe it's named for him. Could be. I don't really know. Probably. But let's just say that the farad is an odd unit. It's based on coulomb. It's based on a really large value. Remember, 1 coulomb of charge is a lot of charge. So a 1 farad capacitor is a big capacitor. Takes about 1 coulomb of charge to stop the heart. So you get yourself a 1 farad capacitor. All you need is 1 volt to charge it up. Keep in mind, a 1 farad capacitor used to be about the size of a garbage can. When I used to... So, a farad is a large amount. We have today found ways to make capacitors much smaller, and mostly it's using more exotic materials, ways of enhancing the electric field outside of just the shape and structure of the device. But ultimately, making a capacitor hasn't changed very much in the last couple hundred years. The best way to make a capacitor generally is to find 2 pieces of metal, make them really, really thin, and get them really, really close together without touching. Now, the important detail here, they can't touch. The moment they touch, they're no longer a capacitor because they can't separate the charges. The moment the 2 conductors touch, the charges will equalize. So if ever you've plugged something in and you've smelt or seen the little blue smoke come out, generally that's a capacitor that's failed. And when a capacitor fails, it will oftentimes discharge through the capacitor, igniting whatever the fluid is that's inside the capacitor, and it usually comes out as a little puff of blue smoke. Don't smell it, it's toxic, but it smells horrible. It's nasty stuff, and your device will never work from that point on. If you guys who have maybe built gaming machines or gaming computers, or have any kind of desktop computer, if you open up the inside and take a look at the motherboard, you'll notice a whole group of electrical devices that look like little cylinders. You'll see them grouped together at one side of the motherboard. Almost all of those capacitors are located right where the power connects to the motherboard. They are designed to take the electric potential that's coming in from your power supply and make that power available for the rest of the computer. They're also designed to ensure that the power coming into the motherboard is uniform. There's always slight fluctuations that come in because they're trying to convert the power from AC to DC. Capacitors can help equalize the flow of charges to make sure they are very steady DC. If you ever see any brown goo on the top of one of those, you should be aware that your computer board's about to fail. You've probably got 2 to 3 months left before it is rendered completely useless. And there will be no recovery from that, no matter how much you spent on it. Fair enough? So, about 5 years ago, actually I guess it's more like 10 years ago, an entire batch, so we're talking millions of capacitors, were put together improperly and were shipped out to all major motherboard manufacturers. So in the span of about 2 years, almost all of the motherboards built with those capacitors failed in the same 2 years. Huge server farms went down, enthusiast computers, you name it. It was terrible. They traced it back to a single lot of bad capacitors. All right, so let's talk specifically about how to make a capacitor. Generally, the most successful capacitors are parallel plate capacitors. Those are the most successful. And although we will talk about others, the parallel plate capacitor is the one that we talk about the most. Now, a parallel plate capacitor sounds exactly like what you would expect. It has 2 plates of metal that are kept parallel to each other. Ultimately, we're using a parallel plate because what we would like between the plates is a uniform electric field. If you remember way back to our discussion about an infinite plate of charge, you should be able to tell me what the electric field is from an infinite plate of charge. It's in your notes. I'll wait patiently. And I have an idea of a volunteer or two who'll be able to tell me. Knew I could count on you. This is the electric field near an infinite sheet of charge. Yes, please commit this to memory. Now, in order to understand what we're about to do, I want to remind you that capacitance is defined by how much charge can be pushed between two conductors based on an applied voltage. And although that's kind of what we're going to do, what we're actually going to do is assume that we have already charged the capacitor, and in so doing, created an electric field. We're going to use the shape of the electric field to help us define the capacitance. This is why we have spent so much time talking about electric potential and electric field for different shapes. So, the first thing I needed was the electric field near an infinite plate of charge. Because even though a parallel plate capacitor isn't an infinite plate, we are going to assume that we are dealing with two plates that are very close together, so that a point in the middle might as well feel as though it's near an infinite plate. It's not. And we know it's not, but we're going to assume that it is. And to do that, you have to understand a little bit about what's going on here. First, the positive plate should have an electric field on both sides, like so. But the negative plate also is creating an electric field. And it's creating an electric field inwards on both sides. Now, if we extrapolate that just a little bit, we realize that on the outside of the plates, we will have opposing electric fields. And this will be true on both sides. Remember, the electric field near an infinite sheet is a constant. And since the two plates are charged by taking charges from one plate and moving them to the other, it can be assumed that the positive charge from this plate is equal to the negative charge of that plate. This is a lot to take in, I know. But if you pluck one electron from the plate and move it to the other plate, you do realize you would create an equal amount of both positive and negative charge on each plate. Does that make rational sense? So if I take enough charges to get 1 coulomb of charge available on the positive plate, that means I must have moved 1 coulomb of negative charge to the negative plate. Right? There's charges conserved, so for every electron I need to account for where it went. So capacitors, when charged, will have equal charge on both plates. They'll just be of opposite type. Also, if we assume the two plates have the same area, then the charge density for each plate must be equal and opposite. Because the charge density is charge per unit area for a plate. This suggests that when we charge the capacitor, the plates will have a charge density equal to sigma. So if I want to know the charge on a plate, it'll be the charge density times the area. Am I going too fast for you guys? Are you following where this came from? I just took the definition of charge density and solved it for charge. Now, stop again and say the definition of capacitance is based on how much charge you get per potential difference. I have just found an expression for the charge on the plate based on the size of the plate and the charge density. I've done that very specifically. As a step in this process, you need to find a way of expressing the charge in terms of something that defines the field. Since I knew the field was defined in terms of the charge density, I tried to find an expression for the charge in terms of the charge density. Luckily for you, there are only 3 types of capacitors on the planet. So once we've done this 3 times, we've covered them all. Is you okay so far? We only have to do this once for a parallel plate capacitor, and it will be true for all parallel plate capacitors. So I just spent a few minutes finding a way of expressing the charge in terms of the size of the plate and the charge density. Now, I don't need to prove this to you, but I want you to understand that we've designed this purposefully so that the electric field outside the plates is going to be 0. But 2 plates contribute to the electric field between them. The positive plate and the negative plate both contribute to the electric field, so I get 2 times the electric field inside the plates. Because they are lined up, they just symmetrically add. Since this is the expression for the electric field near a parallel plate capacitor, the electric field inside this capacitor must be sigma over epsilon naught. And it's a constant. Savri, what you got? Do you have a question? All right, so again, what we're going to try and do, and thank you, Melissa, for catching me in a lie, is we want to find the electric potential by integrating the electric field from the place of low potential to the place of high potential. This is the convention and how you should do it anytime you're faced with calculating the capacitance. But like I said, there's only 3 shapes. So once we've calculated all 3 types of capacitors, we've kind of done all the jobs. This is the easiest. And part of the reason this is the easiest is because the electric field is a constant, making it a pretty easy calculation. Now, dr is a distance. The dot product merely gives us direction. We are moving against the field. It's going to provide us with a cosine of 180 degrees. That's what the dot product's going to do. Now, and we've kind of done that once or twice already. But the important thing here is we are going to need another variable, something that tracks how far we've moved in going from one plate to the other. Lucky for us, the electric field is uniform, so it doesn't really matter whether we go from here to here or we move from here to here. Since the electric field is the same everywhere between the plates, all we need to do is have a straight shot from one plate to the other. We are going to have to know, though, how far we're moving. So I will create a new variable to keep track of that. D, the distance between the plates. Since they are parallel, this distance is the same everywhere between the plates. So my integral will be going from 0 to d. And normally I tell you all I have to do is set up the interval and we'll be done, but no, we have to execute this one. But there's not a lot to do here when it comes to executing the integral. V equals minus integral 0 to d of E, the electric field. That is sigma over epsilon naught, which is a constant, times dr times the cosine of the angle between dr and the electric field. So if we are going this way, and that's dr, and the electric field is in the opposite direction, that will be the cosine of 180 degrees. All of that complication just to tell us that we are going in a direction of increasing potential. That going from the negative plate to the positive plate will increase the electric potential. Now, all of that is a constant. None of that changes while I'm integrating. It's the same. So all I have left is the integral from 0 to d of dr. Well, the antiderivative of 1 times dr is just r. That's all I have to do. So negative sigma epsilon naught cosine 180 degrees r evaluated from 0 to d. I'm getting to the bottom of the page. Would it be too much for me to just write the answer right here as sigma d over epsilon naught? Is that okay? The negatives cancel out between the cosine 180 and the negative sign. Executing R from 0 to D is just D minus 0. And I still have my sigma epsilon naught. That is the electric potential between two plates, period. I'd say memorize it, but it's really not that big a deal. I have no idea. Now, we just found the electric potential caused by the electric field from between two plates of a capacitor, which means sigma d over epsilon naught is the electric potential. The definition of capacitance can then be used to figure out what the capacitance is for a parallel plate by just doing substitution. I can't do it here. I'm going to have to go to another page. Is going to have an electric field that's not so uniform at the edges because it's not infinite. So real capacitors will have a slightly different capacitance than what we just, but C equals Q over V, where V equals sigma D over epsilon naught and Q equals sigma A. Sigma is the charge density of the plates, A is the area of the plates, D is the separation of the plates, and epsilon naught is the permittivity of free space. So when I plug all of those in, I'll get sigma A over sigma D over epsilon naught, which yields, cancel out the sigmas, I'll get A times epsilon naught over D. This is the capacitance for a parallel plate capacitor. Your textbook shows that without proof, but I believe that the proof is important. It shows you where this comes from. We assumed that we could charge up a parallel plate capacitor by moving charges. We therefore were able to show what its charge would be in terms of the charge density. From there, we knew what the electric field would be, so we could calculate the electric potential. And when we plugged all of it in, I will point out that we now have an answer that has nothing to do with what the charge was on the plates, nor the electric field inside. If you look closely at this, this is all geometric in nature. Do you guys notice that? This is just geometry. A represents the surface area of the plates. D represents the distance apart. If I want to build a capacitor, I need plates that have a lot of surface area and are very close together. That would give me the largest capacitance. Right? It's just geometric now. Epsilon naught is the permittivity of free space, which means I need to hold a vacuum between those two plates. That part's hard to do. But all it really means then is I just have two pieces of aluminum foil and don't let them touch. I've got a parallel plate capacitor. Now, there are some issues with this. First, we dealt with what's called an ideal parallel plate capacitor. We made an assumption that the plates were infinitely big, and we know that that's not true. We know that there are limitations. Real capacitors have what are called edge effects, in that a real capacitor proved. However, if you can keep the plates really close together compared with their area, you get really close to this value when calculating it. In fact, we're going to do this lab later this week or early next week with just aluminum foil and textbooks. And we'll be able to show that you get really close to the value. Now, it's hard to get the plates close together without having them touch. So generally, we are unable to have a vacuum between the plates. We usually have to fill it with something. And here's where I have to introduce a new term. You see, most plates tend to be two pieces of metal on either side of some filling. Something that will intentionally hold the plates apart. The filling we call a dielectric. Here's the amazing thing. Almost every material on the planet is a dielectric. And a dielectric is a material that enhances the permittivity of free space. I'm going to say that again because I'm trying to use my words carefully. Almost every material on the planet is a dielectric. And a dielectric is a material that enhances the permittivity of free space. Meaning my filling has its own permittivity. Notice I got rid of the little knot there. I just put an epsilon. Materials are measured by the ratio of the permittivity of the material compared to the permittivity of free space. Almost every material on the planet has a permittivity greater than 1. Greater than 1. Meaning this ratio is better than 100%, which means almost every material in the universe does a better job at establishing an electric field than a vacuum. A vacuum does the worst job of establishing an electric field. So if we put anything between the plates, it's likely to make the permittivity higher. Which means if I want to increase the capacitance, you'll notice that permittivity is in the numerator. If I fill the plates with anything but a vacuum, I will get a higher capacitance. So a piece of paper would be better than a vacuum. And a piece of paper is incredibly thin, allowing me to get the distance really, really, really small. So when I say that we're going to get our plates close together and they're going to look like infinite plates, I want you to imagine you can have a piece of aluminum foil that maybe is, 50 centimeters on a side. It'll have a huge area, and it's only the width of a piece of paper apart. That's a lot of capacitance. All right, you've seen all the theoretical for capacitors. Everything after this, dielectrics. That's what I want to talk about first. Dielectrics. So this symbol is for the permittivity constant, which, as we've talked about, is 8.85 times 10 to the negative 12th. And that's, let's get those units right. Coulomb squared over Newton meter squared. The permittivity constant establishes how easy it is to set up an electric field in free space. Almost every material on the planet has a dielectric constant, or has a permittivity that's greater than this value. So we define something called the dielectric constant, which is lowercase kappa. And just to be, clear, the Greeks, lowercase kappa is an entire K located below the dotted line. That's lowercase kappa, I know. Pretty awesome. So that when you write the dielectric of a material, it's written as a dielectric constant. This is a unitless quantity. And it represents the ratio of the dielectric of your material to it represents the ratio of the permittivity of your material to the permittivity of free space. It's called the dielectric constant. And since I totally tripped over my own words a couple of times, let me say that again. It represents the ratio of the permittivity of your material to the permittivity of free space. The dielectric constant is a unitless quantity. So, when we solved for the capacitance of a parallel plate capacitor yesterday, and we got the area times the permittivity divided by the separation distance, the truth is we should add kappa in here, because it is almost impossible to make a capacitor with a vacuum between the plates. It's almost impossible. The way you actually make a capacitor so that you can get the value of D really small tends to be to take a piece of metal, and you can use almost any conductor you want. So generally we use a conductor that isn't like silver or copper or gold. We use something that's more malleable than that, and we use something that you can etch one side. We're talking about chemically etch. And then they allow it to oxidize. Because if you chemically etch it and allow it to oxidize, a layer of oxygen atoms will basically adhere to the etched side so that you can then sandwich it between another plate. This gets it very, very close together. We're talking about a couple of atoms apart. So the value of D can be really, really small. In some capacitors, it can be measured in maybe tens of angstroms, 10 to the negative 10th meters, 10 to the negative 8th meters. That's how close together you can get the plates of a parallel plate capacitor. And the interesting thing is, since we're getting it so close together for plates that are pretty big, we don't worry about the edge effects hardly at all. The fact that it leaks along the edge, that the electric field isn't particularly uniform around the outer edges of this little sandwich. So we take it, and then they roll it into like a Swiss roll. A Swiss roll. So that there's a couple of layers of chocolate cake with a nice little filling inside. That's what a capacitor looks like if you take the plastic off. You dip the whole thing in an insulating plastic, so you get something that looks like a cylinder like this with a little skirt at the bottom. It's just the extra plastic, and then there's usually two wires hanging out. Bless you. Today's modern capacitors are called electrolytic capacitors. So when we actually work with capacitors in class, which will be next week, we'll be using the ones that I have, which are all electrolytic capacitors. They will have one wire longer than the other. The longer wire must be connected to the upper potential of your battery, and the shorter wire goes to the lower potential of your battery, because they use a dielectric that is actually keyed in one direction to enhance the field only when it goes one way. There's some materials that have very high dielectric constants if the electric field is applied in the right direction. They use polarized molecules that are all lined up already to help enhance that electric field. Does that make sense? So if you use a polarized molecule and the molecule is lined up already, you can help increase the size of that electric field, making for a much larger capacitance. We're going to be using 1 farad capacitors, but today's 1 farad capacitors are small. They're like the size of the top of this marker, as opposed to the old days where they were massive. The issue is that my 1 farad capacitors that we're going to use for the lab are of low voltage. Bless you. They cannot handle like 12, 15 volts. They can handle like volt. So they're low voltage, high capacitance capacitors. They work perfect for our labs next week. So that's what you look like when you see capacitors. Generally, capacitors about the size of your pinky are going to be in the microfarad range. If they get smaller than that, they're going to stay in the lower microfarad range. They also make disc capacitors that are made out of ceramic. They look like ceramic discs. They just look like little coins, but they're brown because they've been dipped in a ceramic. They're going to be in the picofarad range. So microfarads, picofarads tend to be the range of capacitor that we work with in reality. So a lot of your homework problems are going to use real sized capacitors in their discussions. you should expect to see microfarad and picofarad. Micro 10 to the negative 6, pico 10 to the negative 12. Those are the two most common size capacitors that we see. The symbol for a capacitor, there are basically 2 or 3 different ways a capacitor is drawn electronically. The most common is to draw it as a parallel plate, just like that. So a battery, a single cell battery should look like this, with a smaller line and a wider line. The smaller line is supposed to be a little thicker than the wider line. It's to represent the anode and cathode, positive and negative of your battery. Capacitors, 2 lines should be the same size. It is quite plausible you'll be asked to draw an electronic diagram on your exam. It doesn't happen often, but if you have to draw a capacitor, do not confuse it with a electric potential or a battery. Sometimes in the literature, you'll see capacitors drawn like this, with one of the lines curved. There's no difference. However, if it's an electrolytic capacitor, they will specify positive and negative in the electronic diagram. Capacitors don't have any special codes on them. They are stamped with their capacitance right on the label. So you'll be able to read off your capacitance right from looking at it. You don't need to know any special resistor code or anything like we talked about last year, that the colors on resistors mean something. But you do have to be cognizant that almost every capacitor will have a voltage limit. So when we break out the capacitors next week and you grab them, if you blow a capacitor, I won't be mad. They're not expensive, but they're toxic. So if you pop a capacitor, you need to let us know so we can put the evac fans on to get the gas out of here. So that's the symbology we will use. I'm not going to talk a whole lot about the electronic part of capacitance. We have a few more things to talk about theoretically, but capacitors can be connected both in parallel and in series. So connecting capacitors in parallel will look like this, while connecting capacitors in series will look like that. And this is not necessary that you know this. This is on your equation sheet. But capacitors in parallel add together, while capacitors in series add as inverses. So for those of you who had physics last year, this is the reverse of resistors. And the reason shouldn't be all that weird. Capacitors in general, no matter how we look at them, will always have something about the area divided by something about the separation distance. And yeah, there'll be a scaling value, but it's almost always this ratio that determines the capacitance, no matter what their shape. So when you have them in parallel, it should look as though you are increasing the total area. That's why the capacitance goes up. And when you put them in series, it should look as though you are increasing the overall separation distance, and that's why it goes down. Now, the last thing I do want to tell you, and this is incredibly important, I will say nothing more important than this today. By definition, capacitors in parallel must have the same potential difference across their plates. Regardless of the situation, capacitors in parallel will have the same potential difference across their plates. Charges will flow until that happens. There's nothing the circuit can do about that to change that. Capacitors in series will have the same charge across their plates, or on their plates. So here, the potential difference across the plates will be the same. Here, the charge on the capacitors will be the same. Since capacitors are judged by their ability to store charge for a potential difference, knowing when the potential difference is the same versus when the charge is the same is a critical piece of knowledge. Begin memorizing it now. Yes, sir?
Aren't those the same for resistors?
Resistors are similar. I'll say similar because resistors don't store charge. So for resistors in parallel, they have the same potential difference. Right. The analogy to charge is charge flow for resistors. They would have the same current. So yes, you don't have to memorize anything new. Charge flow and total charge are the analogy for capacitors. All right. That's just a brief part. We'll be hitting this. You'll be hearing this song over and over again. We're just hitting the top parts of capacitors. Yesterday, all right, we developed that the capacitor has two ways of describing it. There's the theoretical term capacitance, which describes how your collection of metal behaves when connected to a potential difference. And then there's the pragmatic capacitance of a capacitor, which we only talked about a parallel plate capacitor. This relationship is like Ohm's law for capacitors. This relationship is like Ohm's law for capacitors. While this is how to make a capacitor. Now, I'm not going to make a lot of comparisons here, but if you were paying attention at all last year, then you know that Ohm's law related resistance, current, and potential difference. While we did have a way of calculating how to make a resistor, the Plato lab, where we made a resistor out of Plato, and we showed that the thickness of it reduced the resistance, but the length of it increased the resistance. So we have an analogy between capacitors and resistors. Today, what I want to do is I want to try and firm up something we did yesterday. And that is to talk about where capacitance comes from and how it's calculated. And we did the parallel plate one yesterday. Today we're going to do the coaxial cable. And it's a little bit harder, but I think we can start with I think we can do the coaxial cable together as a group. Coaxial cable as a capacitor has an inner conductor and then has an outer conductor. So, how many of you have coaxial cables at home? Should be probably most of you. This is the predominant way that the cable company gets their signal to the cable box. So if you have a cable box at home or a DirecTV box at home, how many of you have, I'm not trying to call you out about your social economic being, but who knows what I'm talking about when I say cable boxes? All right, so it's most of you. Most all cable companies send the signal through coaxial cable. Does anybody have a box? Do you guys know much about your stuff at home? So you let your parents set all that up and you just go downstairs and operate the remote control? All right. Well, if you've been the person stuck with having to deal with all this stuff at your house, generally cable companies are old school. They distribute the signal around the house using coaxial cable. Part of the reason is coaxial cable is really, really effective at sending signals without getting much interference. It's very effective. HDMI is not nearly as effective. But HDMI has to carry 16 wires. The same data is carried serialized over a coaxial cable. The cable box just splits it all up. Instead of sending it in serial, sends it all in parallel to 8 different sources, which is why HDMI is kind of a complicated standard. The coaxial cable is able to manage all that data because they can send it at much higher voltages, and therefore they can send it with more tightly packed data. That's what it means to say serialized. They're sending one little piece at a time, but they're doing it in a very fast pace all in a row. coaxial cable self-shields, and we know this because we talked about Faraday cages. There's an outer shell and an inner shell. So, unfortunately, or fortunately, depending on your usage here, coaxial cable acts like a big capacitor, which means you can fry your electrical box if you're not careful with the way you use your coaxial cable. Cable companies know this, and so they tend to turn a blind eye to it. They ground all the lines. So the outer shell for all the coaxial cables are actually tied together outside and grounded to prevent the buildup of electrical energy in the cable lines that run through your house. Because you probably have hundreds of feet of coaxial cable run through the walls of your house. Every place there's a wall fitting that has a coaxial plug-in, there's probably 100 feet of cable to get to that wall fitting no matter where it is in your house. So if there's one in your bedroom, one in a living room, one in a secondary living room, one in another parent's bedroom, all of that cable can store energy just like a capacitor. Well, that's bad news, generally, so they try to discharge them. Today we're going to talk about how a coaxial cable can act like a capacitor. To do so, I want to draw two pictures for that. I want to draw first looking down the barrel of the coaxial cable. So this is the outer shell, and then there's the wire itself, which is in the center. There's that centered. Good enough for you guys? Now, I want you to imagine this is very, very long compared to this separation distance, which we'll call capital R. Also, I drew it big, but let's assume that the inner wire is actually pretty small. That way I don't have to worry about how thick it is. Is that okay with all of you? It just adds a complication that's really not necessary. But, you guys are smart enough. Let's go ahead and say that, just for fun, that there is an inner radius that we'll call R1 and an outer radius we'll call R2. This way, you're seeing the real thing. Okay? Now, again, let's say that this whole thing is very long compared to this distance. Is that all right with all of you? All right. First, I want you to remember that if you have a very long wire, that it will have an electric field, assuming we charge up the inner wire, that looks something like that. In fact, having already done Gauss's law, you should be able to write out what the form of the electric field of an infinitely long charged wire is. Do you remember? We use lambda over, am I jogging your memory enough? Yes, sir? Yeah.
Is it lambda over 2 pi epsilon naught?
That's it. And R.
There's R.
Yeah. The infinite wire is proportional to 1 over the distance. The point charge, 1 over the distance squared. And the infinite sheet is constant. That's basically what they are. I mean, yeah, you have to know the 2 pi epsilon naught. It's nice to know that too. But its point charge is 1 over the distance squared. Line is 1 over the distance. And an infinite sheet is constant. So no matter how far away you are, the electric field's the same. So this represents the electric field inside or near a long conducting wire. So what we're going to do is consider this again. Let's assume we have a very long capacitor, say a capacitor of length L, and there is negative lambda on the outer shell and positive lambda on the inner wire. To calculate the capacitance of this kind of capacitor, our process requires that we do two things. Find an expression for the total charge and an expression for the electric potential. Our hope is to have these two expressions be in terms of the same variables, like, I don't know, lambda. That's our goal. And this is how we calculate what the capacitance of a shape is. So the first thing I will point out is that if we have a very long wire that has charge density lambda, the total charge on the inner wire or outer wire would be lambda times L. Does that make sense? Any question about that? Excellent. Our next job is to try and establish what the electric potential would be between the inner portion of the wire and the outer shell. We've not done this before. So we're going to calculate the electric potential. Now this would actually be the calculation we would make if we were trying to find the electric potential near an infinitely long wire. And I'm going to go to have some space, so I'm going to get another. Our capacitance gets bigger as the two wires get closer together, just like a parallel plate capacitor would. So, place here to work. And just to have a point, remember the electric field coming off of this wire is lambda over 2 pi epsilon naught times R. So we're going to find the electric potential by integrating the electric field dot dr. And to determine the electric potential, just to remind you, we go from the place of low potential to the place of high potential. Which means that we are taking and moving a charge from where the outer wall is towards the place of high potential. Now, quick facts. We are moving with a dr in this direction, but my electric field is out. So the particle is being moved against the charge. So my dot product here is going to produce a cosine of 180 degrees. This is to show that the particle is being moved against the field and therefore is increasing the electric potential, increasing the potential energy. Next, we're going to drop in our expression for the electric field. And as discussed last week, we're going to try and collect all the constants to leave just the part that has to be integrated. Can you guys figure out what all the constants are? So basically, all of that stuff. So I'll get negative cosine 180 degrees times lambda over 2 pi epsilon naught times the integral of R2 to R1 of 1 over R dr. My expectation is that you could follow all of that. Maybe not construct it yourself, but you could follow along with all of that. Deriving the capacitance is not something that is easy nor intuitive, and you won't get much practice. Because how many shapes are there? I told you yesterday. There's 3. Yeah, this is number 2. So after I do the next one, you've seen every possible way to make a capacitor. So at this point, there's math in front of you. Math that you might not be particularly good at. I'm going to go to another page just so I can write that out. And -1 times cosine of 180 just strips away the negative sign. You guys okay with that? So I get lambda over 2 pi epsilon naught, and the integral from R2 to R1 of 1 over R dr. Now, I am very confident that many of you don't know how to take this integral. We can't add 1 to the exponent like we would have if it was a normal polynomial. This is r to the -1. The antiderivative would have us add 1 to that, which would be r to the 0, and then divide by our new exponent. So we can't use the polynomial rule here. And some of you have not done this yet. And that's okay with me. You don't have to know. You will have to be able to do this integral by the end of the year for the exam. But my assumption is that you don't know how to do it right now. But that doesn't mean you can't learn. The antiderivative of 1 over r is the natural log of r. If you don't know that, put it in your notes, because you need to. It shows up more often than any other integral in this class, including sine and cosine. Which means when I find this antiderivative, I would write natural log, and I'm going to do what your math teachers do, even though it's a little bit redundant. They put it in absolute value brackets. That's pretty redundant. And your math teachers, I have found that Mr. Brashear and Mr. Bright, neither one of them talk about why they put the absolute value signs there and why it's redundant. So I'm going to tell you, it's redundant in our class, 100%. Can the radius ever be negative? Can we ever go inside negative space somehow? No, it's redundant. This can never be negative. That's just to prevent it from being a negative number, because if you don't know this, you can't take the logarithm of a negative number. Now, my experience for most students is they don't fully understand what a logarithm is, but they know most of the logarithm rules. Is that your experience? You know the rules, even if you can't tell me what a logarithm is. So I'm okay with that. For the time being, as long as you know, I, in this class, will probably never write the absolute value bars. I'll forget, even though that's technically true. But because we exist in the real world, our radii will never be negative. So to me, it's a wash. Now we're going to keep going with this, but this step was new to you today. But I'm going to need you to know that I need that skill set from you. So please begin to commit it to memory. It is on your equation sheet. So if you look up the integral table on your equation sheet, this one appears there. So my expectation is that you can do it now. We have to have it next week when we do capacitor circuits, when we introduce differential equations. So at this point, you are supposed to know what to do next, which is to plug in your limits. And here's where I expect that you guys know more than even that you are aware of the natural log rules, which means I can write this as a quotient. That the difference between two logarithms is the logarithm of the quotient. Now, I don't know if you remember that or not, but now you know. I've refreshed your memory. You guys good for that? because we're actually pretty much done now with finding the capacitance. We've done all the really heavy lifting. As I said to you before, find the capacitance of a shape. You have to see how the charge on the capacitor is related to the potential difference it creates. That's what we did. We said, let there be charge on the capacitor, equivalent to lambda. That was the charge density. And then we calculated the electric potential it would create in the space around that charge, which was lambda over 2 pi epsilon naught times the logarithm of R1 over R2. This leaves us with an expression for the capacitance. I'm going to clean this up, if you don't mind, by canceling out the lambdas and leaving 2 pi epsilon naught times L over all right. Now, that's the expression of the capacitance of a cylindrical capacitor. That's what we would call this, a cylindrical capacitor. Now, there are 3 types of capacitors. There is the parallel plate capacitor, the cylindrical capacitor, and the one that we probably will do, but not for a while, the spherical capacitor. Not that it's hard, it's not. It's that you can't make one. How do you make you can't charge up the inside of a spherical capacitor because you have a ball inside another ball. That's a spherical capacitor. So we don't make those. On the other hand, we have found that a single ball by itself can act like a capacitor. The Earth does. The Earth collects charge, it acts like a capacitor and discharges into space. So the Earth stores electrical energy because of this. So we know that these things exist, but they're not real devices. These 2 things are real devices. We build these. We use them in the laboratory. We use them for electronics. But which one of these is easier to make? The one on the right or the one on the left? Yeah, it's hard to make cylindrical capacitors. They tend to be made by accident. And so we tend to try to force them not to exist. We don't want the buildup of charge usually in most of our cylindrical capacitors because they're cables that connect our electronics together. So we tend to not want those to happen. But the parallel plate ones we make all the time. Now, I will say a few things about it. They don't look like they're the same, but they actually are if you look at the things they have in common. Do you notice they both have an epsilon naught in the numerator? Do you guys see that okay? And so I could replace that with kappa epsilon naught if I fill the space with anything else but a vacuum. The 2 pi is kind of funny. It's circular. That's why it shows up. Have you noticed with anything that's circular, you get pi in there somewhere? And anything that's cylindrical, we tend to get a 2 pi. And anything that's spherical, we tend to get a 4 pi. And that's because of surface area. So cylinders, it's always 2 pi times something to get the surface area. And for spheres, it's always 4 pi times something. So it's not accidental. When we deal with this, it's always about area. Now here's the funny part. Funny's the wrong word here. Do you notice that on the right side, the units are length for A over D, right? Meter squared over meters. Do you notice that the logarithm is a unitless quantity and L has a unit of length? So this is still the same units of meters. And the bottom gets smaller the closer R1 gets to R2. That's, if you go back to our original picture,